I learned something about physics this past Thursday. For
Yeah.
half an hour.
What'd you learn?
I learned that gravity is a cruel mistress.
Yes.
And to take a look on those.
What?
I'm missing an angle.
Oh no.
Yeah.
I determined at a young age that gravity was cruel because the thing that I wished to do, like watching superhero stuff, the single thing that my heart wants most to do is just fly. And gravity's preventing that. So I went into physics, partially to try to figure out how to circumvent the laws of physics. I've yet to do that. That said, gravity's nice because it's better to be attached to this planet than it is to be drifting freely through space. Okay, so a couple of minor announcements. One, schedule and calendar stuff. Email went out recently announcing some rest days added to the calendar, which I'm very glad for because the last 12 months have been somewhat of a fever dream for most of humanity. So I think we should all at least get some kind of vacation. This week, it's pretty normal. Classes will be as normal. We will have normal lab. Next week, which is both the last week of March and the first week of April. School-wide, there's no classes on Good Friday. That doesn't affect this particular class at all, but do enjoy it. One of the announced rest days is Monday the 5th, so we have a 4-day weekend, which would be nice. Also doesn't affect this class specifically, but given that of the 4 days between, 4 of the days between when I see you and when the homework will be due are given to resting, and that's the point. I might delay the homework that week anyway, even though we'll still have all of our class meetings, just because I assume no one's going to be doing anything productive that weekend,
You're correct.
including me.
Does that mean the second exam's not going to be on the 6th anymore?
Yes, the second test will not be April 6th. Second test will not be April 6th. I foresee it being pushed probably about 2 weeks, actually. I want to make sure to get through magnets before we spend a week or two looking at waves and then final exam. I might end up abridging magnets though, because I really want to talk about light and sound with you guys. So, first part of April is going to be finishing up circuits, looking at magnetism, etc. This week, these 2 weeks will largely be normal for class because none of the days off affect any of our meetings. The next week, we have Tuesday the 13th as a rest day off, which means we will be meeting here for lecture and we won't have a lab that week either because it's cutting the Tuesday out. So, class meetings are pretty normal until this point, wherein no class this day and no lab that week. And I would foresee the next test being around that week. Excuse me. So there will be a test middle or end of April about all the electricity and magnetism stuff. As for the short term, currently the Chapter 16 assignments are listed as being due tonight. I'm actually going to go ahead and move them to Thursday on the grounds that I was working on the other lecture and we found some of their questions made me realize that some of the questions on the homework weren't always great in terms of like how the points were fairly balanced, or that like A and C were good and made sense, but for some reason B didn't on one of the questions. So I'm going to be adjusting some of the point values, kind of omitting some parts of questions. I might add one other question into the assignment just so that there's still more points there total. And just because of these changes, I'm pushing for Thursday. So 16 homework and quiz are now due Thursday. That said, if you have any specific questions about those things or would like to begin today by looking at those. Main bulk of today's lecture, my plan is to begin looking at Chapter 17 material. Chapter 17 assignments are currently slated to be due, well, I guess at all things optimal, it would be Tuesday the 30th. If it needs to be pushed back, I will. The homework for Chapter 17 is already up. It is labeled Chapter 17.1. It's because that's a notation that I put in because I have multiple copies of each chapter that I'm working on and tweaking. I want to keep the old copy for records, and I need to get the second copy a different name. So since it's the next iteration, I called it Chapter 17.1. So the 17 assignments will be titled 17.1, but that is the assignment. We're kind of as normal. So, excuse me. What we're going to focus on this week is electrical current, electrical resistance, and the resistor circuits. Any questions about logistical stuff before we open the floor to Chapter 16 homework questions? Okay. Speaking of, any questions at all about Chapter 16 homework assignment? That, if I'm remembering correctly, is one of the ones that people were asking about that I need to tweak slightly.
Were the first two the same for you? Well, because it's the same throughout it all. Like you divide, the way it like divides
Okay, so homework question number 4. This is 3 different chunks, more or less. First chunk is combining capacitance. And this is a combo circuit, so you have to take it one step at a time. I like to work these kind of from the inside out. Excuse me. C1 is in series with these two, which are in parallel to each other, which are then still in series with C1. So that is a combo circuit. You have to do at least 2 operations before you can find the final answer. When looking at these circuits, I find it helpful to kind of trace what the current's going to do through them. So from one end of the battery to the other, current goes through C1, then splits here, goes to either one of these two before remerging and going to C1 again, or the other C1, not the same one. And that tells us that C1 is in series with the lump sum of 6 and C2, even though 6 and C2 are parallel to each other, and those 2 chunks are themselves still in series with the other C1. So part 1 is just find the total capacitance. Part 2 is find the charge on each capacitor. Part 3 is the voltage drop across each capacitor, which the way that I am accustomed to teaching electricity, I cover voltage drops as part of a resistance. So we're actually going to be talking about that starting this week. I might have mentioned it in passing, but I haven't indicated really anything about the math involved with that. So part C, I'm going to reduce the point values for this part of the question so that it's not, because just by virtue of this having 9 blanks in it, the assignment's going to weight this as higher, even though each of these pieces are really small, and these ones I want to be even smaller because I didn't teach you how to do this yet. So I'm going to set these to 0, probably set these to like a 1/4 point each. Does that make sense? So main thing to focus on is making sure you can find the total capacitance.
Are C1 and C1 in parallel to one another?
They are not.
Can you tell me why?
I can't tell you why. And actually, I'm going to now look at the other two hybrid circuit questions because I have, why isn't it centered? Oh. There we go. Okay, so 7 and 8 are also hybrid circuit questions. And 7 and 8 are also hybrid circuits. And I don't know if that bothers me too much. Why am I like this? There we go. So these are also hybrid circuits. They're more complex ones, so I feel like these will be good practice. For combo circuits like this, I like to trace the path of the current because it kind of helps show what should be in series or in parallel with what. Now, if things are in series, it means that the current flows through one of them, and then that same current has to then flow through the second one. This can be drawn a couple of different ways. For example, this would be series, but things can also be in series even if there's a bend in the wire. So if the current was coming in through here, then the current would pass through this capacitor, then it would pass through this capacitor, and it would keep going. So even though these wires are drawn parallel, geometrically speaking, these capacitors are in series with one another. Series is dictated by current going through one, and then the same amount of current going straight on through the other. Parallel, meanwhile, for two things to be in parallel with one another, the current will split before reaching either of them. The split current, each branchway will have current through it separately, and after going through each one, the current will then remerge and continue on. And I usually draw the rungs as being parallel, like geometrically parallel to one another, but like how I could definitely easily draw a series circuit where the capacitors are drawn geometrically parallel to one another. There's several ways to make a parallel circuit that don't involve wires necessarily being geometrically parallel to one another. This would be a parallel circuit, among other strange examples that I can think of if I wanted to. Current comes in, splits, goes through each element, remerges, and then continues on. Sorry, this is a symbol for a resistor. Do that one out of habit. So, looking at each of these questions quickly, the drawing only shows part of the circuit. It just shows the chunk with the capacitors in it. So, for consistency, I just drew in where the battery would live. And in this particular circuit, current exits the battery. It's going to enter into the circuit through the A node. Current from that point is going to travel down. It's going to hit this junction and it's going to split. So up to this point, there's been no capacitors yet. We've not talked about anything in relationship to one another. At this point, we're splitting. So we're entering a parallel zone. Current could go left, travel through C1. If it does this, it's going to have to travel through C2 before it remerges, which means that C1 and C2 are in series with one another. Same thing with this right branch. You've got a C1 followed by a C2. The middle branch just has the C3 in it before the current remerges. So, of these three branches that we've traveled through, the three branches are parallel to one another, this left wing, this right wing, and the middle line are parallel to each other, but on those outermost wings, you've got two things in series with one another. Does that make sense so far? Okay. If it doesn't, just let me know. The current's going to reemerge at this spot, keep traveling, then it's going to split again right here. Some of it's going to go through this C2, some of it's going to go through this C2, are coming back together, and then continuing on. So these two C2s are in parallel to one another. However, this whole assembly right here is in series with this whole assembly right here. Because after the current's done with this whole block, it then has to go through that next whole block. So there's a lot of different things that are in series or parallel with other different things. I like drawing the current through everything. It helps shed a little bit of light on what's in relationship to what. And after that, I then begin working it from the inside out. We want to try to simplify things, one element, one rung at a time, compressing elements together so that there's fewer of them, and working your way out from the inside. Looking at this particular question, the first thing I would recommend doing is taking the C1 and the C2s on the top. These two are in series with one another, so we can perform the series operator and find one capacitance for the both of them. I'm just going to call that CA since the numbers are already taken. The other rung will have the same total capacitance because it's also a C1 and a C2 in series with one another. But we still have C3 untouched in the middle, and we haven't looked at the bottom part yet. Once we've done that, now we just have three things in parallel with one another. We can add them together normally and compress them into a single capacitor. Now, looking on, we have these two down here that are in parallel with one another. We can compress those to a single capacitor. And after all that simplification, now we're just down to two sum total capacitors that are in series with one another. So we can perform the series operator on whatever we count for B plus whatever we count for C. Sure. So just looking at this. Now that we've combined the C1 and the C2 together, the C1 and the C2 were in series. So we did the series operator to find what CA would be. So 1 over total CA is 1 over C1 plus 1 over C2. C1 and C2 are in series. We perform the series operator. Find what CA is. CA is the equivalent of both of these in series together, which means we can rewrite the whole thing with them combined as CA. And since the other rung has a C1 in series with the C2, they will also combine to form the same number. Now, still just looking at this top piece, now in this simplified version, we just have three capacitors in parallel with one another.
So we just add them?
Yes, we can add CA, C3, and CA to create what I call CB. Question?
Actually, you can finish going through this, because this is not.
Okay. We can compress these to CB. We can't go any further with CB yet because it's in series with this. So we need to simplify the bottom element first. The bottom rung, the bottom element, has two C2s that are parallel to one another. So we want to perform the parallel operation on those C2s. So call that one CC, 1 over CC is going to be 1 over C2 plus 1 over C2. As a general rule, no wait, they're parallel. That just adds together. Never mind. They're parallel, they're just going to add up normally. So CC should be C2 plus C2. Since we know CC, we perform the parallel operation with that and CB. Because there's a million different possible hybrid circuit combinations, so there's not always going to be a general formula of, start with this run, figure it out. Which is why I like doing the current, tracking the current to help establish the relationships between each of the elements. And my next advice is always simplify from the inside out. Yes?
So then the final circuit that we made, it would just CB and CC would be in series with each other?
Correct.
Okay.
You know they're in series because any current that goes through CB will come out and then has to go through CC.
Okay.
Number 7 is similar, although fewer elements are present. Number 7, we've got the split. We have one branch and we have just the 6. The other branch has a C and a 3 micro farad in it. Then the current reemerges and we've got 20 in series with everything else. So I would draw that. Let me stretch it here. I would combine the first two on top that are in series. Then that combination is in parallel with the 6. Perform the parallel operation. And now we have whatever, the entire first square in series with the last one. Yes.
So, sorry, for number 8, to find CA, we would have to do 1 over C1 plus 1 over C2.
Correct. And after you add up their inverses, you need to take the inverse of that sum.
Okay.
Because if you look at it, it's 1 over the total C is 1 over C1 plus 1 over C2. So you add these together, you're going to get some tiny fraction number. You're going to have to invert it so that we have C equals number, not 1 over C.
So that it's CA that we get. Okay,
Correct.
and not 1 over.
And one of the reasons these ones are uniquely tricky in WebAssign is it just says, look at this, tell me one number. And if that one number isn't right, the computer's just going to yell at you and you don't get any productive hint out of it. So please, 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 if you're having issues with it, send me your work. I'll tell you, you're doing it right, but you need to tweak something here. I will tell you how each of your steps is going so the WebAssign doesn't just endlessly get you frustrated. Because I'm generally not a fan of when WebAssign just has, one answer, do all your work, put your one answer here, hit or miss. I don't like that, but it's just the nature of the format. And I want to be available to you to help you with the work so that this doesn't become as frustrating as it might end up being. Because, well, see, I look at this and I see a puzzle, and my brain likes puzzles. I understand that not everyone looks at this and gets the same kind of weird kick out of it. So, please, 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 send me your work and your questions. If you have any issues or questions about it. That's one reason why I'm extending it to Thursday. The other reason I'm extending it to Thursday is I'm going to tweak the point values on 4. I'm also going to tweak the point values on 5 because this middle question doesn't really make any sense. Like, doesn't make sense to me the way that it's written, which means it's definitely not fair to make you guys sit and try to think about it and figure it out. What's probably happening here is this textbook was just written by 2 to 3 very tired, very underpaid physicists. I'm sure it made sense to them. I'm sure you can find this answer. I just can't tell the method by reading the question by itself the way that it's written.
Didn't we do one in class like this?
Well, the potential. Well, this is the potential energy of the pair of charges. I assume it would be the energy from, like, the sum energy from one charge, both charges added together, like the energy of one in the other's field. But it's asking for a negative answer, and I don't think you should be able to have negative potential energy. So I just don't like this part B.
That's fair.
A and C aren't bad. B is the part that makes me go,
And then you said 4C we don't have to worry about right now either?
Correct. So I'm going to be making 4C worth no points, 4B worth reduced points, and 5B worth no points. I can't really remove parts from a question, from an assignment that's already been posted, but I can at least drop the point values. Yes.
Okay. For 4B, I thought I was doing this right, and it's told me I'm wrong in really big red letters more than
Oh,
once. What is the equation that we're supposed to be using for this? Because maybe I'm just using the wrong one.
Okay, so charge on each capacitor. The formula in question is capacitance equals charge over voltage.
Yes.
The problem is that, and this is something that I normally talk about with resistors, which is why I haven't really mentioned it yet, which is why I'm going to actually, I shouldn't reduce them, I'm going to take part in that as well. Problem here is you're using the right formula. You are using the right formula. C equals Q over V. The problem is, in a series circuit, not every capacitor is being exposed to the full 9 volts.
But in parallel,
In parallel, they would,
here.
not in series. And again, my brain, I naturally, organically talk about this with resistors, capacitors first, because that's the order in the textbook, which means I haven't mentioned this yet, so I'm going to be dropping RV as well. But the elevator pitch, which will be going more over this week, is in series, the voltage drops after each element of the circuit, because the voltage is kind of like the water pressure, and some of the pressure gets used up pushing the current through. So each of the individual capacitors has a specific potential difference across it, and that's the voltage that goes here, not the total 9 volts. So really, which is another reason why I don't like this question, because this, part C, should be before part B, because part C is finding that potential difference before you have to use it. So, note to the editors, these two should be swapped, but I'm going to be reducing the points of these questions because I didn't talk about how to do that yet, and I apologize. The book is clearly going in a different order than the mental order that I am used to working in, so I am sorry. I just am talking about resistors first next year. So, 4 and 5 are the ones on this assignment that are going to get tweaked and have parts dropped from them. And I may add another question on just to make up for that. So for all these reasons and more, the due date is being moved to Thursday for the homework and the quiz. Well, quiz won't need to be, I'm sorry, didn't thought. Due date is being changed to Thursday. Keep working on them. Please send me any issues that you're having. We'll spend some time Thursday looking at things again what we're gonna do. That sound all right?
Sounds like a plan.
Okay. I would like to begin looking at resistors so that we have some of this preliminary knowledge before lab today. We're about halfway through the lecture period. Does anyone need water, questions, brain break, etc.?
So are we starting chapter 17 notes right now?
Correct. And beginning chapter 17 material, do still focus on making sure you understand you can finish the chapter 16 stuff tonight, but time dictates we at least start 17 now for lab and such.
When are you going to post the chapter 17 notes?
Ideally very soon. I'm sort of overhauling how 17 works because resistors are spread across 2 or 3 different chapters of the textbook. And so I'm going to be taking those chapters and pulling all the resistor stuff out of them and lumping them into all just this slideshow. So there's a little Frankensteining I'm still doing before I post them. I apologize. My plan is to have them up today. Okay. So, we're going to look at and formally define electrical current and electrical resistance. These, in my opinion, are what actually makes up the bread and butter of most circuits, which includes the wiring of all of your dwellings, the machines you plug into the outlets, etc. So, electrical current is the electricity. So current is the literal flow of electrons. It's like the flow of water, we call water current. The flow of electricity, we call electrical current. So in all circuits, in all machines, the actual electricity itself, the flow of the electrons, is called the current. So current is defined as the flow of... So I found out that this is Edison's fault. Way back in yon colonial era, Edison formally established and defined, we had some particles that were positively charged. We had particles of two different charges. He wrote a paper about that. He arbitrarily decided the ones over here are positive, the ones over there are negative, and I'm going to base every single piece of math I ever do on what those ones I call positive are doing. All of electricity is arbitrarily, from the proton's perspective, basically because Edison did a coin flip. And he got it backwards, because the electricity itself is moving electrons. In spite of this, every textbook, every diagram is always going to show electricity flowing like positive charges, flowing out of the positive side of the battery, around the circuit, into the negative side. It's infuriating because the exact opposite is what actually happens, and yet all textbooks, all pieces of information still acts on this assumption because of one colonial man made one mistake and we based everything on that mistake. Oops. I assume most of you have heard the word amp before. So the unit of amperes is the measure of current specifically. So 10 amps is the amount of current traveling through something. We derive this unit based on this formula. For some reason that I still don't actually know, the variable for electric current is a capital I. Yeah, current starts with C, the variable is I, and yet the unit for current is amps with an A. I don't invent this stuff. Current is equal to the flow of charge over time. Literally, the formula is the definition. Charges are moving in some amount of time. That's what current is. And the assumption is if 1 coulomb of charge flows in 1 second's time, that's going to be a total of 1 amp. You know how you'll never actually encounter 1 coulomb of charge in real life because that's just too dang big? It's the same with amps. 1 whole amp would set fire to everything because that's just too much current traveling through one object. So in most of our circuitry, we're dealing with milliamps or smaller. There is not anything bigger than 1 milliamp running through your phone at the moment. 1 whole amp is dangerous. Current in general is the dangerous part of electricity. You might see, on an electrical box, danger, 10,000 volts. The voltage is not the problem. The current is the problem. Voltage is just water pressure. But water pressure means nothing unless there's water flowing. Bless you, sorry. Current is the actual moving electrons, and the more current there is, the more electrons that are traveling, and the faster they're traveling. The more electrons and the faster they're moving, the more energy they're carrying with them, and the more energy they leave behind in whatever they're traveling through. which is why when a tree gets struck by lightning, tree gets set on fire, because literally energy from the electrons is now in the tree. The tree absorbed energy from the electrons, and when wood absorbs energy, it tends to combust. So, all this to say, current dangerous, 1 amp is dangerous, no touch.
What happens in our bodies then when we're electrocuted?
Great question. So, let's say I knew I was about to get struck by lightning and I could not avoid it. What I would do is raise my right arm upwards, lift my left foot so that the direct path is just from my hand down my leg, my right leg. Current is going to enter through my hand, and current is always going to try to go into the earth. So current enters my hand, electrons surge down my body, preferably down my right side because there's fewer vital organs in this part of me. So the current is just going to travel down the shortest path through me, through my leg, into the earth itself. All of those electrons are moving very, very fast through my living tissue. And so they're leaving energy behind inside my living tissue, boiling the water inside of me and scorching a few things. I don't necessarily recommend it, but I am under the impression, at least an amount of you are going into medical careers, and I've seen pictures of lightning scarring. It literally looks like the victim was torched from the inside out. The lightning scar is burning on the inside of you. And it looks like what you'd expect lightning would do to a person. So, the reason I would recommend doing this is so that all that damage happens on the side of you that doesn't have your brain and your heart.
Then why does sometimes it really doesn't do like a whole lot to the person and they're fine?
It's always going to depend on how much current it is, how much voltage there is as well, where it enters them, and where it leaves them. If you just get like just a hand stun gun just on your finger, the current is only really going to travel from one prong of the stun gun through the length of your finger out to the other prong. Your finger is going to hurt, but it's not going to do anything bad to your brain. It's always relative based on the specific strike. So, to avoid lawsuits, don't tase someone in the head. That said, some current will still travel outwards, and the really nasty part of being shocked is, and I might not be describing this totally medically accurately, since our muscles basically operate on electricity from our nerves, when you get a serious enough shock, all of your muscles just start tightening up at once like they're all being activated, and you just freeze and lock up because they're all activating at once and nothing ends up moving as a result. So the danger of like touching live electrodes is you touch them, you're getting shocked, your muscles freeze up, and you can't pull yourself away.
What does it feel like when you get tased?
Very similar, I assume. I have not actually had it happen to me, but when being tased, current is traveling through you, and the goal of the taser weapon is that your muscles lock up and you can't do whatever you were doing before you got tased.
So if some tased you for like a really, really long time, would it eventually like burn you?
Yes, because current is charged over time. The longer the current is applied to you, the more electrons surge through you, and the more energy they leave behind.
So if your muscles lock up, then why do sometimes people like pee when they get tased?
That might be a different muscle untensing.
Yours-
Or
the
maybe the
same
muscle that
bladder
pushes the
naturally.
urine out tensing. I'm not
And so
entirely
when
sure.
tased, it releases it.
Point is, your brain is no longer in control because the lightning is what's now triggering your muscles, not your brain. Again, I'm less familiar with the medical side of all those sentences, so take all that with a grain of salt, several grains of salt. I can speak more to the electricity part and the muscles part. Okay, And for safety's sake, all of the circuits we're ever going to use in here will have very low voltages and incredibly low currents. Okay. We'll do that later. So. So, electric current is what actually travels through things. Current and voltage team up to form the bulk of what's happening inside of a circuit. Voltage comes from the battery. And when you wire up a circuit, you're creating a path from one side of the battery to the other. Let's say this is a 3-volt battery, plus, minus. When you wire up a circuit like this, you allow current to travel from one side of the battery to the other. And because every single book on the planet is going to treat it as though it's coming out the positive side, I'm going to continue that notation, even though I hate it. So current comes out of the battery, circles around, and then comes back. Current is the electricity itself. So voltage drives the current. The current is the electricity. And all that's left is to talk about the specific object that the current is passing through. So, voltage drives electricity. Electricity. Current is electricity. The last thing that you need to make a circuit is resistors. Battery is always going to drive current to be moving, but current always has to flow through something. You can't get electricity just going through nothing, which is why you don't see lightning bolts arcing through empty space. Electricity always has to travel through some other substance, kind of like sound waves need air to travel. Every time you've seen electricity, that was current traveling through air. So electricity always needs a medium to travel through. And whatever that object is technically a resistor in terms of how it fits into this 3-part unit that I'm about to describe. Yes?
Current is what electricity?
Current is electricity.
Oh.
So voltage pushes current through stuff. And the thing that the current is being pushed through is a resistor that has resistance. Every single object that you can run electric current through counts as a type of resistor. Whenever you build a circuit, I'm going to build a light bulb here. You build this circuit, you plug in the light bulb, current travels through the light bulb, the current leaves energy behind inside of the light bulb. And so the light bulb is acting as something called a resistor. Every single object in the universe has some amount of electrical resistance. And resistance is defined as an object's ability to prevent current from flowing through itself. Pardon me. Everything has some amount of electrical resistance. It's just a question of if it has a lot of resistance or a little resistance, or maybe something in between. Something with high resistance does not let electricity travel through it super easily.
So like insulator.
Correct. Exactly. An electrical insulator stops electricity from traveling through it. What is the first electrical insulator you can think of? Rubber. Very good. That's what all the wires we work with are coated in, because it is an insulator current does not easily travel through it. So rubber has very high resistance. On the other hand, metals have very low resistance. We call those conductors instead of insulators. So objects with resistance are important because one, we can use objects with high resistance to stop current from going where we don't want it to. B, we can use objects with low resistance to send current into things that we do want it to go. And then there's objects with kind of middle resistance, like this light bulb. Every single thing has some resistance to it because every single object has some measure of electrical resistance. That includes rubber, steel, wood, the human body. Humans, considering that we're full of water and carbon, humans actually conduct pretty poorly, thankfully. And it's because our skin is designed as an insulator, both a thermal insulator and an electrical insulator. This is one reason why you can be touching two ends of a battery and feel nothing. Your skin is just doing its job. That's why you shouldn't lick a battery, because your saliva conducts a lot better than your skin does.
Wait, what happens if you look at water?
Zap.
So
I've
they
done
say,
that
it's
before
never
when I
happened
was
to
a
me.
kid.
Now, the trick
No.
is you have to lick both ends of it at once, so you really only see people trying with the 9 volts, the rectangles with the 2 probes on top. My dad always told me, hey, lick it to see if it has charge. I was too scared.
You almost got it.
Sometimes, like, if my iPhone charger, like, if it's plugged in and it, like, rests on my arm for a minute, like, just because I'm not paying attention, it'll, like, it hurts a little bit.
Well, that's not okay.
No, it's, like, happened, like, I've woken up and, like, my arm would be, like, on the charger, and I would feel like it would
Does
just
it,
hurt.
okay, is it heat pain, or is it
I don't
tingly,
know.
sparky pain?
I feel
I'm
like
just
it sparked,
curious.
it was a little sparky.
Okay.
Like, it was
Is that
very,
bad?
very light, but it was, like, enough that I was like, okay, I wouldn't want to keep my hand on here.
Because in humanity's quest to charge our cell phones faster and faster, we've probably been upping the amps on those chargers, which would make them hurt more. If you up the voltage and you up the amps, you can get to the point where it might actually hurt someone. And since people just want their phones to charge faster, the companies are just trusting people not to lick them.
No pain, no gain.
No. Okay, so every single object is a resistor. When you plug a light bulb or a vacuum cleaner into a circuit, you are technically plugging in a resistor. Because resistors, this is kind of a circular definition. Resistors resist current passing through them. And they take energy away from the current.
So it's sort of like shadows.
Kind of.
It's like the current is like a metaphor first in this case.
I really like using water as an analogy. Imagine the dam is the resistor. You've got a big rushing, raging river that suddenly comes up against the dam. Some of the water gets through, but once it does, it's lost a lot of its energy, it's lost a lot of its oomph. Now it's just a gentle stream. The dam, the resistor, kind of told the current, hold up a minute, and took some of its energy away. The current that makes it through, because current does make it through, in order for it to be a closed working circuit, some current has to get through. What does get through though is just lower energy. It takes energy away from the current. And this is why all of the machines you plug into a circuit are resistors. The machine draws energy from the current, takes energy away from the electrons. Now the energy is powering the machine. I use light bulbs a lot as an example because current runs through the gas or the filament of the light bulb. Energy from the current gets left behind in the gas or the filament, and that makes it glow. I dropped the markers. Yeah, get it later. So, every device plugged into a circuit acts as a resistor. This little kind of Charlie Brown EKG squiggly line is the symbol for resistor. This is still the symbol for battery. The symbol for capacitor is the two same length parallel lines. This one's resistor. So in any circuit diagram, this represents the things plugged into the circuit that are getting powered by the circuit. This could be the light bulb, could be the laptop, etc. That said, like with capacitors, there is also a physical thing that you could have bought from Radio Shack called a resistor, a little component that you can plug into a circuit. These are used to manipulate the current and the voltage in the circuit to be a specific output for other things you plug into it. For example, do I have one on me? This is my switch charger, my Nintendo, for my video games. And these things that sometimes happen on the plug or sometimes are a brick in the middle of your laptop cord, these things are full of resistors. The goal being that those resistors take the current that it's getting from the wall and tweak it so that what actually ends up in your machine is what the machine needs and it doesn't fry.
Then why, if you just plug the cord into your laptop and into your phone, it doesn't have anything like that?
The brick is modifying what it gets from the wall. I call this a brick. I call all those blocky things bricks. That's designed to take what the wall is outputting, which is a very specific current and voltage that is American standard, and tweaking it to be whatever the battery of your system needs. I assume the industry standard for other devices that get passively powered through USB cables, that this laptop is designed to output a specific amount of current through that cord, which the phone can handle. The brick is just to change what the wall gives you. And you'll see them in lab this week. The actual component resistor, they look a lot like capacitors, but they're smaller. They kind of look like a little dumbbell. It still has the little metal legs coming out of either side so that you can plug it into something. These are noticeably smaller though. They're like this big. And they've usually got sort of like tan plastic casing with different colored stripes on them. And this will be part of what we're doing in lab. Since they're so small, you can't really write on them. So instead, we use colored stripes in a certain key code to help figure out what each resistor is. Resistance is measured in units of ohms. Resistance is measured in units of ohms. It's spelled like this, but the symbol for ohms is the Greek omega. So any capacitor you buy at the store might be listed as 10 resistor you might buy at the store will be rated in how many ohms of resistance it has. And 1 ohm of resistance is incredibly teeny tiny. So tiny that it basically, like, the most conductive thing on the planet has somewhere between 0 and 1 ohm of resistance. Most things in nature will have somewhere between 1,000 ohms of resistance to a couple squintillion ohms of resistance. So the actual things we're going to be working with in lab will be about 1 kilo ohms, about 10 kilo ohms. Humans have several thousand kilo ohms, a couple hundred kilo ohms worth of resistance because of our skin. Yes.
What is that?
Oh, thank you. This is a different formula that I would like us to focus on there. Right now, I want us to focus on this part, because this will be more immediately relevant to lab. The reason that I've listed those 3 things in conjunction together is because voltage, current, and resistance set what is happening with the circuit. The relationship between these 3 things, it's written up here as I equals V over R, but sort of the more classic way to write it is V equals IR. Subsequently, you can do I equals V over R, or you can do R equals V over I. Any way you write it, that formula tells you what is happening inside of the circuit. The voltage driving the current through the circuit's resistance. Oh, there we go. I know I've been rambling kind of straight since we started this particular set of notes. Main takeaways to definitely have in your notes to be working on lab this week. You got definitions of these 3 things: voltage, current, and resistance. Know that resistance is measured in ohms. Have this formula, V equals IR, because we're going to spend lab looking at how we use this for whole circuits and how we use it for individual parts of a circuit. Last thing I want to touch at least briefly on is the circuits themselves, because resistors can be wired in series or parallel as well, like with the capacitors. The difference is how those resistors add up in each circuit type. With capacitors, when you run capacitors in series with one another, that drives up the capacitance of this. That drives down the total capacitance of the circuit, because they kind of work against each other. One ends up blocking the next one. And if you run capacitors in parallel, you drive down. Sorry, I'm going backwards. Capacitors in parallel, you drive up the capacitance because they're all acting as parallel plates. With resistors, it's exactly the opposite. So remember the formulas, but they're swapped. So resistors in a series circuit, the resistances all add up linearly to determine the resistance of the entire circuit. The reason for this is resistance is the measurement of how hard it is for the current to make it through. So if you're just stacking obstacle right after obstacle, right after obstacle, that just makes it harder and harder for the current to get through. And that drives the resistance up. In parallel, meanwhile, when you have parallel rungs, you're giving the current a multiple choice option on where to go. The rung that has the lowest resistance, like whichever rung has the smallest resistor plugged into it, is going to be the rung that most of the current goes through, because that's the easiest path. And so having multiple options inherently drives total resistance down. You're giving multiple pathways. Imagine, like, well, it's a little bit of a... Okay, imagine at a big assembly, the lecture hall has 3 different doors. One of which is the big one. Most people are naturally going to gravitate towards the big door. There's more room, more people are going through it. But some people could also take smaller side doors, fewer of them, but some of them could take those doors, and that's fewer people having to go through the big door. By having multiple doors, you're making it easier to get out. So we're going to be doing similar math, but the logic is kind of reversed. Any questions today? Okay. Lab this week, we'll be going over this material both in lab and in lecture. Do be working on chapter 16 stuff first. Actually, make sure you're done with and understand chapter 16 before you move on. We'll address any questions you have about that. Either you can send them to email, send them to me via email, or we'll talk about them in the lecture next time. Great days coming up. I'm excited about them, and I hope you guys get to enjoy them. And I'm just rambling at this point. Have a great day. If you have any questions.
I'm coming back, I'm just looking at stuff here.
Never let my rambling stop you from leaving.